So, in many ways, this is the most important part of the nuclear physics and also the syllabus generally. This is a megally important part. And why is it so important? Because it contains the two most important experiments possibly ever done in physics, certainly ever done in nuclear physics, and the two most important processes, maybe not important to us just now in the terms of being able to do them, but important in the sense that they created life. So, fairly important, all in all. The first experiment was done by Ernest Rutherford. Now, Rutherford, who I always think looks a little like an older version of Freddie Mercury, if Freddie Mercury had survived. There he is with his Freddie Mercury moustache. What you basically have here is Rutherford's gold foil experiment. He had the idea of bombarding a very thin piece of gold foil. Now, they used gold not because they were particularly precious. Haha, double joke. Not because of that, but because they could get gold really, really thin. Literally 4 atoms thick. Gold has the ability of forming something called a leaf. This is literally beaten into shape, but it's very, very thin. And he wanted to see what was the interaction between the alpha particles, which he didn't realise what they were, he didn't know what they were at the time except they were positive, and the gold, which obviously he thought were atoms. So he sent the alpha particles through thinking he'd get quite a bit of scattering. What actually happened, of course, was that the vast majority of particles went straight through, missed the gold atoms altogether because the tiny, tiny, tiny nucleuses. And he worked out from this that because 99% of the alpha particles went straight through the nucleus, went straight through the gold leaf and didn't get deflected in any way, he said the nucleus must be very, very small, which was true. He was right. But some of the alpha particles bounced back. Now, he discovered this when I had an argument with two of his research assistants, who said that there was no point in looking at it would be a waste of time to looking at the ones that would bounce off and come backwards. But he said, no, look. And when they looked, they found them. And he said, well, what that must mean is that the nucleus not only is very small, but entirely positive, which at the time was impossible, because they hadn't discovered a force which could hold an entirely positive object together, that they thought electric repulsion would pull it apart. So he had discovered that the nucleus was very small, that it was entirely possible, and discovered the last great force to be discovered, the strong nuclear force, all in one experiment. So a very important experiment. This experiment proves that the nucleus is small and positive. Now, the two students he was having an argument with were Cockcroft and Walton. Now, this would already be a megally important experiment if it wasn't for the fact that dear old Mr. Warner, Warner? I don't know who he is. Walton was in fact Irish. He was a fellow of Trinity Dublin. So, and remains the only Irish citizen ever to win a Nobel Prize in Science. There is a gentleman who lives in Canada, who's a Canadian citizen, was born in Ireland, who can rightly claim as Irish, I think. I don't think we have any problem doing that. But he was the only Irish citizen, the person Irish at the time, to win a Nobel Prize. Absolutely brilliant experiment, this. Cockcroft and Walton hadn't found a way of accelerating particles. They just used sources, and these were sources which already existed. But they weren't getting anywhere. We weren't getting anything done. So Cockcroft and Walton artificially accelerated a proton using a very high electric field which they themselves had designed. So they invented the particle accelerator, and then they did the first experiment with it, in which they smashed protons which were being produced by a hydrogen discharge tube and then accelerated by this enormous electric field into a lithium target. When it hit the lithium target, it turned into 2 alpha particles. Now they realised that the alpha particles were actually helium nucleuses. So they turned hydrogen, a proton, and lithium into 2 alpha particles, helium. They had changed one element to another. Now, people have been trying to do that, turn lead into gold, for millennia, literally millennia. And it was called the Philosopher's Stone, this idea of turning one element into another. Well, this is the first experiment that ever did it. As well as this, they then were able to prove in the laboratory for the very first time Einstein's E equals mc squared equation. So another absolute mega experiment which, you simply can't overstress. The alpha particles were detected because they produced little flashes of light called scintillations on a zinc sulfide screen. And you could look down a microscope and see these flashes. And it was exactly the same microscope and flashes screen as used in the previous experiment by Rutherford. So there's two experiments. Rutherford proving the nucleus was small and positive, and Cockcroft and Walton being able to proving that you could change one thing to another and proving E equals mc squared as well. Brilliant experiment, though they're probably best remembered among physicists for building the first particle accelerator, which was used by everybody afterwards and always gets credited to them. Rightly so, they did do it. Here's Walton. That's him in his later years, enjoying his fame as a Nobel laureate. Nice smile, Also very fond of children. I think he had 13. Anyway, Nobel Prize for Physics. And he got it really for this. Proton, which is the hydrogen, plus lithium goes to two alpha particles, one going in either direction, and the energy. And the energy was E equals mc squared. It proved E equals mc squared. And it was also the first transmutation by artificial bombardment. Transmutation means turning one element into another. And there is the formula, which you can see the top adds up to 8 and the bottom adds up to 4, and they have to add up, and it's very easy. And my God, what a simple expression. And I'm afraid you have to remember that one. That's one of the very few things you have to actually just remember, because it does come up. You can work it out sometimes, and sometimes they say, what is the whole thing? And you have to kind of do it. So what they'd been working towards was this idea of binding energy, the idea that the nucleus is held together by a binding energy made up with a loss of mass. So in order to hold the nucleus together, you lose a little bit of mass. The mass which is lost is converted into energy by E equals mc squared, and this energy holds the nucleus together as the strong nuclear force. Now, you might remember in junior set you were told energy can't be created or destroyed. Well, that's not true. E equals mc squared says energy can be created, and it can also be destroyed and turned back into mass again, which we'll talk about in the next topic. But, I don't really like that one. I don't like energy conservation because we know it's not true. I've no idea why we still teach it. Oh, well, maybe I do have an idea and I just don't want to say. So, iron is the most stable element, and everything that moves towards iron releases energy. That's why you've got fission and fusion. Essentially, if you are uranium, you are over there. So if you break into smaller bits, you're moving that way. That's fission, the breaking up of a heavy nucleus into two smaller nucleuses with the release of energy. If, however, you are in the sun and you are hydrogen, then you are forming helium, which is doing the same thing. It's going to a lower energy form, a more stable nucleus. And in that case, also, you release energy. That's why you can get energy by breaking up a nucleus, fission, or by joining two light nucleuses to form one heavier nucleus with the release of energy, fusion. That's why you can get energy from both processes, because they're not the same elements doing it. And you're heading towards the goal, iron. Iron is the most stable. And if you're moving towards iron, you're always going to get some energy out of the reaction. So if you split up a big one and get close to iron, or you join together a lighter one and you get closer to iron, you get energy out in both cases. And I'm not going to bore you with this, but basically it's the formula. We usually take, there you are, atomic mass units. Now, I'm not going to expect you to go through all of this. I just want you to see that what they've actually worked out in this equation is the difference between what a deuterium, which is basically an isotope of hydrogen containing a proton and a neutron, the difference between its mass of, if you put the two things together, and the actual mass. There's an actual difference, here it is down the bottom here, a difference in mass between the mass of a proton and a neutron and the mass of deuterium, which makes it up. Which is a bit like, if you took, 4 marbles, you weighed them individually, and you put the 4 marbles in a cup and weighed them, you'd say, oh, well, the weight of the cup. Yeah, I should have said that differently. If you got 4 marbles physics and you weighed them individually and then you weighed them all together, no cup, forget the cup, they would have a different mass. They would be lighter. And of course they won't. In Newtonian physics, they're not any lighter. But in Einsteinian physics, they are, because they need something to hold them together. And that's the binding energy at the bottom. And we can find out how much energy is by, first of all, we have to turn those units, which are just used for atoms, we have to turn them into kilograms by conversion. That's very easy because this conversion factor is in the logbooks, and we just multiply the number we get. You see, that was the number from the previous one, by the conversion factor, and we get a number in kilograms. And then we put that kilograms as the m in E equals mc squared. The c, of course, is the speed of light squared, and we get an energy. Now, that looks very small, but you've got to remember that in every gram of hydrogen, there are 6 times 10 to the 23 atoms. So if you were to get that much from every single one, you would end up with something like 6 times 10 to the 10 joules, which would be probably enough to create a rather large hole in the planet. So, and that's from a gram of hydrogen. So you can see that the amounts of energy involved here are absolutely fabulous. And that's because although each individual atom produces a tiny amount of energy, there's an awful lot of the buggers. So let's look at the two forms of energy release again. The one that happens in the star, which causes the universe to exist, life on the planet, all those minor like things. A fusion. This is where two isotopes of hydrogen join together to form helium. In this case, I've got probably the simplest one, which is also probably the least likely to have produced an awful lot of energy, which is deuterium. Two deuteriums bash together and form a helium, you see. If you put those together, you get helium in the middle there. Of course, it doesn't happen every time, and it's very difficult on the Earth because we can't create the pressures of the sun. We can create the heat, definitely. In fact, we can easily create a lot more heat than is in the sun instantaneously in these colliders and things like that. But we cannot produce the pressure. And so we have to ramp up the temperature even hotter and hope we can make fusion. Now, we can do fusion. Fusion is possible. I mean, there's fusion bombs, the hydrogen bomb, etc. But the problem is that it takes more energy to do than we get out of it. Now, as soon as we get more energy out of it than we put in, then we've got a process which will change the world. And I still hope it'll happen in my lifetime. Though, you know, they better get on with it. I'm not getting any younger. Well, yeah. Anyway, fusion, the joining together of two like nucleus to make one nucleus with the release of energy. Fission, on the other hand, is the old-fashioned uranium or plutonium bomb, where they take a very heavy nucleus, they split it into two smaller, more stable nucleuses with the release of energy and usually neutrons. So neutrons are also produced. So a neutron bombards something like uranium-235, which then breaks into two daughter nucleuses. Notice I'm saying nucleus and not atom or particle. It's always the word nucleus. We're doing nuclear physics for a reason. It's nucleuses. Anyway, these two daughter nucleuses are produced. There's also a few neutrons produced, and there's also energy produced, and you have to mention all of them. Okay. And here is the thing, you see. You get some sort of neutron. Here we are. That's your neutron. It comes in. It gets absorbed by the uranium-235, and then the heavier thing splits into two, not just with the two daughters. This is probably krypton, and this is barium. Okay, and not just with the two daughters, but also with these three neutrons. Okay, a neutron. And as you might remember, a neutron has a mass number of 1, but an atomic number of 0 because it doesn't contribute. It's not a proton, and only protons have an atomic number of 1 and betas have -1. So that's essentially a fission reaction. Fission as in breaking, like the fissure in a rock. We can also create with these fission reactions rather easily a chain reaction. Now this particularly works for 235. Some of the neutrons you can see, this is the two daughters. Again, I think this is barium, krypton. And here we have the two neutrons, and they're going ahead and producing a reaction in another uranium-235. This is, of course, happening very quickly and causes cities in Asia to disappear. I'm not going to mention the two of them. You know which ones they are. Nuclear explosion now. Luckily, we haven't used them since then. God's sake, we don't really want to. But a chain reaction is a self-sustaining reaction. It doesn't just happen in nuclear physics like this. There are other chain reactions in chemistry, but this is the one we need to worry about. As you can see, there is a neutron starting the process on the far left, hits the 235. The neutrons from the 235 hit another 235, etc., etc., etc. And you get a kind of a cascade effect of self-sustaining reaction where the products of one reaction become the reactants of the next. Self-sustaining products of one become the next. Here's another picture of it, a bit more dynamic with some swirl and some explosive sort of things and lots of marbly-like objects. Quite like that one. Okay, this is the equation. Now, you're not expected to remember this. The most you could ever be expected to remember is the fact that there are 3 neutrons produced. Everything else you will be let have, and you'll be able to work it out. And we'll look at the questions on how you work it out at a later date. But this is a different form of uranium, a different isotope of uranium called 238. This is the one which is more common. You do have to sort of like increase the amount of 235 in a sample by a process called enrichment, even if you're going to use it as fuel just to get it started, a nuclear reaction. But that is not, I repeat, not what you're looking at here. You're looking at 238. 238, the most common isotope of uranium, that is fizzing, it's fissile material here, by a neutron hits it and it does the same thing. It breaks into 2 daughters, krypton and barium, and produces 3 neutrons. Now, the difference is the neutrons it produces are travelling too fast. If they hit another 238, they will not cause a nuclear reaction. So they have to be slowed down. And the material which slows down the neutrons so that when they hit another 238, they cause fission is called a moderator. Now, a moderator doesn't stop the process. A moderator actually increases it, because it slows the neutrons down to the right speed. Now, the most common moderator used in all of the world is graphite, though heavy water, which is a form of water which includes deuterium, can also do a passable job, but graphite's better. So, if you're going to get your own chain reaction, and a good one, that it might melt and form a molten mass that ends up in China, that needs 235. But if you've got 238, you need a moderator in order to make it work, making it a slightly safer reaction, in as much as any of this is safe. Okay, so there you are. Well, let's have a look at the parts. This is a nuclear reactor. You can see the fuel rods. They are in the dark orange, if you like, brown maybe. There's a thing at the bottom. They contain 235 and 238. It's slightly enriched to about 5 or 6% from the 1 or 2% when you dig it out the ground. If you have to enrich it an awful lot more than that to make it into a bomb, which is why enrichment plants are a big sort of bone of contention with countries that are trying to form nuclear power. They always, the nuclear powers don't want them to enrich the uranium beyond a certain point, and they make sure they don't, because then they can't make bombs out of it. Not that most of these people will be able to make bombs anyway. It's quite a difficult process. So you have graphite. There you are, that's in the actual orange. Now that slows down the neutrons so that they can hit another 238 and form fission. And the white lines, they are the control rods. That's boron steel. Now their job is to absorb neutrons and to stop the reaction completely. They drop in, usually by gravity, into the nuclear reactor if it gets past a certain temperature, or it starts to run away in some other method, or the coolant, there's some problem with the coolant. They drop in and they stop the process immediately because they absorb all the neutrons and don't allow any of the neutrons to cause fission. Now, once we've created this, basically all we've done is create a lot of heat. We've just made heat, basically. Just boiled the kettle. And the coolant comes in, takes the heat away and makes electricity out of the heat. So you've just really, I mean, it's just another way of making things hotter, a nuclear reactor, and it's the heat we use to create the electricity. Now, we also have something called a heat exchanger. That's because the coolant, as you can see it there, is radioactive. So we let the coolant run through a pipe, and around the outside of that pipe, we put another jacket with water coming in and out. And that water is then what generates the electricity. So that the coolant from the center of the reactor isn't the same liquid used to turn the generators, because then the generators would get radioactive. So we might even do the heat exchange 2 or 3 times. The third heat exchange, sometimes a bit of a waste, but definitely most of the world they do it twice, just to separate the coolant and its radioactiveness from the liquid used to generate electricity, in which people have to stand next to and not get cancer from with any luck. Now, that's the question. It's a question which is very good to do. It's got everything in it, including something about a heat exchanger, all the other things, how the heat exchanger works, what's the control rods. They're all there. It's actually a really good question, worth doing. It's also got a bit of a calculation down the bottom there as well. Love it. Love it. It's a great question for, like, revision.